Hello students. So continuing the next problem, we have here a cantilever beam with UDL. Okay, so consider a problem of cantilever beam under uniformly distributed load Q naught. So this load Q naught is distributed over the span L. Okay, so the unit will be, if it is the force is Newton, so it will be, and this length is in meter, so this is Newton per meter. Okay, so this is varying as a uniformly distributed load. So I mean, it is not a point load. Previously we have solved a numerical with point load, but here we have a uniformly distributed load. So the governing equation for this problem is EI t to the power 4 v by dx to the power 4 minus q naught equal to 0. So here v is the deflection. Okay, but this is vertical deflection, like this, downwards deflection. Okay, so and we have the boundary conditions given here, that deflection at x equal to 0, that means, see, x is the variable, length variable, this in this direction. This is an 1D problem. Okay, one unidirectional problem. So this is x direction. So when x is 0, so this is the point. When x equal to L, this is the point, when end point, starting point and ending point. So when x is equal to 0, so the deflection is 0 in this case. Okay, and your dv by dx, which is the slope. Okay, v is the deflection, dv by dx is the slope at x equal to 0. That's just at starting point is 0, because this point is fixed. Okay, so there is, we all know that this cantilever beam is going to bend in this manner. Okay, in this manner, right? So this is the beam. Okay, this is the cantilever beam, and the beam is going to bend like this. Okay, fine. So you see, this is the deflection. So here at this point, since this is fixed, so there is no at this point there is no deflection or slope. I mean, deflection is 0, this point is fixed, it is not going down. Okay, so slope is also 0. At this point slope is maximum. Okay, and deflection is also maximum. Okay, so now again another this one is another, sorry, two more boundary conditions are given. Okay, one is d square v by dx square at x equal to L is 0, which is bending moment. Okay, and this is d cube p by dx cube L equal to 0, which is nothing but shear force. So at x equal to L, this is 0 and this is 0. These are the boundary conditions given. So we are given with 4 boundary conditions, and we can make use of them to get the solution for this p. We have to actually, using FEM, we have to get this solution for this slope. Okay, so you see, for this problem we can actually see, you can try with any trial function. Okay, for I mean, but it is actually, it may not fully satisfy all the boundary conditions here. Okay, so you take something like this. So I mean, you will be left with unknowns. Okay, which may be 2 or more unknowns. So here you see, let's choose a trial function like this. V that is a function of x, and your deflection is a function of x, equal to c naught plus c1 x plus c2 x square plus c3 x cube plus c4 x to the 4. So here in this equation we have this is a fourth order equation. So we have taken x to the power 4. At least we have taken an index of 4 for x, so that we can find the we can differentiate it 4 times. Okay, 4 times. So that's why we have taken up to x to the power 4. Next we have from the boundary conditions, we have this v 0 equal to 0 and dv by dx at 0 is equal to 0. So we have, you see, just put you see, these are the boundary conditions given, v at x equal to 0. So what you have to do, you have to find, if you find v0, then you put x equal to 0 in the expression of v. Okay, so dv by dx is equal to 0 at 0 means you have to put when you have to find out dv by dx, and you have to put 0 there. Okay, so then next is what you have to do is, after that then you have to find out again d square v by dx square. Okay, and put x equal to L there to get the whole expression as and put 0 equal to 0 to get the constants. Again what you have to do is you have to find the third derivative and then put x equal to L and equate it to 0 to get the constants. So what you have to do is, you see, simply first using the first boundary conditions. So v0 is equal to 0, so you put x equal to 0 in the expression of v. So c0 plus c1 into 0, c2 into 0 square, so all these things. So this this part will go and we are left with c0. So c0 is equal to 0. Okay, so we get c0 is equal to 0, and dv by dx, if you find for this one, if you find dv by dx, this will be c1 plus 2c2 x plus 3c3 x square plus 4c4 x cube, right? So we have directly put the values here. So dv by dx is 0 is equal to 0. So this is c1 plus 2c2 into 0 plus 3c3 into 0 square plus 4c4 into 0 cube. So here we have c1 is equal to 0. Okay, so I mean this side we have equated it to 0, so c1 is 0 here. So c0 and c1 we have got as 0. So our trial function becomes, after putting c0 and c1 is equal to 0, we have vx equal to c2 x square plus c3 x cube plus c4 x 3 4. Okay, so next time again what we do, we find out. So our expression of v was c0 plus c1 x plus c2 x square plus c3 x cube plus c4 x to the power 4. So dv by dx is equal to c1 plus 2c2x plus 3c3 x square plus 4c4. So these are the expressions for your differential. So all of these we are going to make use. So we have got c0 and c1 is 0 using these two by just putting x equal to 0 here and x equal to 0 here everywhere. So we have got c0 and c1 as 0, and we are going to make use of these two again. So d square v by dx d square v and by dx square at x equal to L, we just put in this expression L here, L here. Okay, so we find out c2 from this. C2 is equal to minus c this expression we have got in terms of c3 and c4, and third you can say this one, d cube v by dx cube at L is equal to c3 6 c3 plus 24 c4 L equal to 0. So c3 is equal to minus c4 L. So c2 from here, if you get, so c2 I mean this, just put this c3 here in this expression. So 4 into 3 is 12, so plus minus minus plus, so c4 L square minus 6 c4 L square. So this is c2. Okay, so replacing the constants in this trial function, okay, what you have to do is, so you replace this c2 here, okay, and c3 here, c4 here. So and after replacing this c2 into whole thing x square plus c this is c3 is minus 4 c4L. So here you replace it and we get multiplied by x cube plus c4 x to the 4. So c4, when you take common this this is the expression we get. So we are left with only one constant. Now you have to determine the constant, and you can then find out the approximate solution. Now you see this is your residual. Okay, residual is just by taking everything in the left hand side and equating. I'm making the right hand side as 0, so the left hand side whole term is the residual. Okay, so this is the domain residual for x. Okay, so just substitute this d4 v by d to x to the power 4. Okay, and that is your 24C4 we have got. Okay, so this is 24C4. all right, so here minus Q naught. So here C4 we have got as this is what you have to do is here you have to find out C4 from this. So you have to make the residual 0. We want to make the residual 0. So for what value of C4 this residual will be 0 is if we find that C4 is equal to Q naught divided by 24 EI. This value will make that residual 0. So the trial solution becomes, in this case, here you see C4, this is the trial solution, right? So we needed the value of C4. So C4 is Q naught by 24 EI. So just put that Q naught by 24 EI. So this is x to the power minus 4 L x cube plus 6 x square L square. Okay, so this is the expression. So this is your trial function. Okay, so this is the problem for UDL. Now if we have a varying load, that's Q naught with respect to x, okay, UVL, then we have to actually make use of Galerkin weighted residual approach. Okay, so next we'll talk about that weighted residual technique that we have actually introduced in the last class. So what we have to do is here, so this is weighted residual technique is nothing but minimizing the residual. Okay, so till now minimizing the residual. So when you make RD is equal to 0, okay, this may not be you can say may not give you the exact solution every time. Okay, or for at one point at another point it will be you can find out the value of that dependent variable, okay, at some points, okay, but it may not be 0 at all the points. So what we do is we want to make the residual, that means residual here is the entire expression. If it's the whatever the residual is, if it is satisfied at all the point, okay, of the span, if it is a cantilever beam throughout the cantilever beam, so if it is satisfied, then it will be 0 everywhere, but it is difficult to get everywhere. So what we do is, in this case, in weighted residual technique, we do not just put this exactly equal to 0, but we multiply something with this, that is called a function. Okay, function f of something. So this is called weighted function W. Okay, or so this weighted function, there may be more than one weighted function, so we just write I here. So I is equal to 1 to the number of weighted functions. So if we take 2, so this is this will be W1 into RD, then another one is there, so W2 into RD, like that, and we integrate it over the entire span. So if the length is L, so this will be L, and if it is a suppose diameter is there from 0 to radius, so this will be from 0 to radius, something like that. Okay, so from the lower limit to upper limit we integrate it, and we overall make this thing equal to 0. So this is called a weighted residual technique. Okay, so here it is written, the weighted residual technique helps in minimizing residual at every point of domain in an overall sense. Okay, so what we do in order to achieve this, we multiplying weighting function Wx and then integrate it over the domain to minimize the residual. So this is what we do. Residual is there, residual will not change, okay, but we have to multiply functions, that is called weighting functions. That is, there may be one, so W1 is one weighting function, W2 will be another weighting function, so there will be more than one integral equations. So 0 to L, if there is, let's say, 3 weighting functions, so this will be W1x into RD dx, this is one equation. W2x into RDx, that is dx, that will be second equation. Then W3 that of x multiplied by RD of x into dx, that is the third equation. So Wix are approximately chosen. These are the weighting functions which are approximately chosen weighting functions. Okay, so now you see, your question is now how to take the weighting function W1, W2, W3, okay, these weighting functions. So we can there is a technique that is your suggested by Galerkin. So Galerkin was a you can say mathematician. So he has suggested that you take the weighting function, okay, weighting function as such that, okay, that is the same as the trial function, okay. So whatever trial function you have taken, okay, that same trial function you take it as weighting function, okay. That's a C naught or something. So that same I mean trial function you take it as weighting function and multiply with that RT. So here you see Galerkin suggested weighting function should be taken as same as trial functions themselves. So here by taking that we have illustrated one numerical, and here you will see that how to solve it, okay, by taking an weighting function, okay. So here you see what is the numerical. Here is consider the uniform bar. Now you see this is the uniform bar again, and this is a actually it will be a cantilever beam, but if we apply transverse load then there will be deflection, but here we are pulling it, okay, along the axis. So consider uniform beam with linearly varying load. This is varying with with x, okay. So q is not constant here. Q is the load, okay. A is any value, A may be 2 3 4, so multiplied by x is there. So when x is equal to 0, that load is 0. When x is equal to L, load will be maximum. In between that, load is increasing. So we are just pulling the whole thing, okay, with gradually varying load, okay. So this is AX is the variable load. This is what I was talking about. So we'll see the use of weighting function here. So governing equation is this AE into d square u by dx square plus AX is equal to 0 with the boundary conditions u0 is equal to 0 and AE du by dx at x equal to L is 0, okay. So these are two boundary equations given. So here you see du by dx is there, so you have to actually whatever trial function you take, that you have to differentiate it once, okay. So here let's see, we have taken a trial function like this. Now see, look at this. This trial function is taken in such a way that c0 plus c1x plus c2x square plus c3x cube. So I told you that you have to at least take a trial function where your order of the variable is at the should be same, okay, or more than the order of your differential equation. So here d square u by dx square, so we could take up to this, okay, c3, but we have taken c3x cube. So this is actually from your, you can try with c2x square also, okay, and you try to find out the expression, but it gives better solution, a better consider it will yield the solution when you take c3x cube. I mean, just to save time, we have taken up to c3x cube. We can take more also, okay, and you can try with that, right? So here you see in this manner, okay, I mean if you take up to c3x cube, so you will get a better solution, okay, better approximate solution. So that up to c2x square term that has been skipped here just to save time. So here you see, so du I mean here you just differentiate it once, so c1 2c2x plus c3x square, okay. So it is there differentiated once more because in the expression we have d square by d square u by dx square. So this is 2c2 plus c3, okay. So now use the boundary condition. So at u is equal to u0 is equal to u0, that u at x equal to 0 is 0. So c0 plus c1 into 0 plus c2 into 0 plus c3 into 0. So c0 here is 0, okay, fine. So du by dx at x equal to L is 0. So this is c1 plus 2c2 L plus c3 L square, okay. So put x equal to L and x equal to L here, okay. So c1 is equal to minus of 2c2 L plus 3c3 L square, okay. So c1 is this expression, okay. Now so put the value here, putting the value in the trial solution, okay, we have ux equal to 0 minus 2c2L plus 3c3L square. So here you see c0 is 0, okay, c0 we have put at this is 0 and this is the expression that we have obtained for C1. Okay, and we have these two remaining. So just now what you do, you rearrange them, and we have C2 x square minus 2lx plus C3 x cube minus 3l square x. Now see, if you suppose you have taken only up to C2, okay, then we this expression would have been modified, okay, and this C3 would not I mean may not be there. Okay, so C3 will not be there if you do not consider, but considering C3, we have some expression associated with C3 and here also. Now what we do is, this will improve our calculation, and that's why C3 has been taken. I mean, one more extra constant has been taken. So now what we have to do is, here we will find out weighting functions from these two, okay, this expression, right? Before that, let's find the domain residual. So this is the domain residual, okay. So here you see, this is the expression. So LH right hand side is 0, so this is itself is a domain residual here. So AE multiplied by d square by dx square. So d square by dx square expression is 2c2 plus c6 c3 x, okay, plus ax. Fine. So here minimize the residual using Galerkin formulation. So now see, Galerkin formulation has suggested, they have suggested that, so you have to multiply weighting function with your residual and integrate it over the span, okay, that make it equal to 0. So whatever, after solving this, you will obtain that secondary variable from here, okay. So sorry, the constants, you will obtain from this, okay. So at what constant the entire residual is 0 everywhere, okay. So that can be obtained by multiplying the weighted function. So here, just to improve the solution, okay, we have taken an additional constant, and the weighting functions will be taken as same. They will be same as the trial functions. So here you see, these are the part of trial functions, okay, that is associated with your constants. So we can try these as, okay, so that means this C2 multiplied by x square to lx, this as first weighting function, plus C3 x cube minus 3l square x, this as second weighting function, okay. These two are the weighting functions. All right, so now that is what we have taken here. So weighting functions are chosen from your trial function itself. So these are the weighting functions. There are two weighting functions, so that we can solve the entire expression. I mean, without one expression, weighting function also, without this also we could solve, but this will improve the calculation. So that's why you see there are two equations now, because first weighting function, that is, now what we do, integration 0 to L w1x into rdx dx is equal to 0. Second equation is w2x rdx dx is equal to 0. So w1 and w2 are there, so put them and get two expressions. So w1 integration 0 to L, this is w1 multiplied by this is your domain residual, okay. So here, by putting the constants and multiplied by dx is equal to 0, this is the first equation, and integration 0 to L x cube minus 3l square x, this is your domain residual multiplied by dx is equal to 0. This is the second equation. So I have skipped the solution part, so you can solve both the equations, and then we'll get the after solving both of them, we obtain that C2, this C2 is 0, okay, and we have C3 is equal to minus a by 6ae. So this is another, you can say, reason, because we have got C2 is equal to 0, okay. So we could not it was observed previously that if we take up to this one, so we will not be able to reach up to a acceptable solution. So we have taken up to C3 x cube, okay. So now you see C3 is minus a by 6ae, but I have to solve, you have to integrate them, multiply all the terms, integrate them, put in place of x we put L and 0, and then we have to solve both the equations, okay, algebraic equations later to get these two constants. So it is minus a by 6a. So putting this thing in the trial solution, so we have c2 is equal to 0, right? So c2 will be 0, so this thing will go, and c3 is minus a by 6ae, so that put here, and then take minus sign inside, so a by 6ae, this will be 3l square x minus x cube. So this is the final expression. So we can keep it like this, or you can just write a by 6ae 3l square x minus x cube. So this is your expression. Now you see, you can find your extension here. Use the extension, right? U here is varying in along with this length. Okay, so load is also varying, so U can be found at any point when x is, let's say, at the middle. So put x is equal to L by 2 here. Okay, L by 2, and find out U. Okay, so this is a better solution, the better trial function. This will give you the value of your extension at any point of x. Okay, so this is the use of Galerkin weighted residual approach. Okay, so we'll talk about one more problem later in the next video. Thank you.